So good afternoon, everybody. Welcome back to the second session of today. It's a pleasure to introduce our next speaker, Ricardo Podestá, from the Universidad Nacional de Córdoba, and he will talk about weight distribution of cyclic code defined by quadratic forms and related curves. Please, Ricardo, go ahead.
Okay, thank you. Well, first of all, I apologize for my English, and I want to thank the organizers, especially Cicero, for inviting me to talk in this nice event dedicated to the memory of Fernando. Right? Okay. So I'm going to talk about the weight distribution of cyclic code, defined by quadratic forms, and at the end, we talk about some related curves. Okay, this is a joint work with Dennis Videla, also from the same University of Córdoba. He was a former student of mine, and we collaborate now. Okay, this is the plan of the talk. First of all, I will review quadratic forms over finite fields. Then I will define some cyclic codes in great generality associated to quadratic forms. Then we are going to focus to some particular family. And then we are going to try to say something about optimal curves. Okay. So, well, everybody knows what is a linear code. We work on the finite fields. P is a prime, Q is a power of the prime. So we consider a linear code of dimension k and length n with minimal distance d, okay, the Hamming distance. And we're going to talk about cyclic code, okay? Cyclic code are codes which are closed by the cyclic permutation of the coordinates, okay? And we are interested in the weight of this cyclic code. I recall the weight of a linear code is the number of non-zero coordinates, okay? And we can put together all these.
Ricardo,
yes.
Sorry to interrupt. There are some requests from the chat. If you could or either speak louder because the people are not listening didn't manage to listen very well, or maybe the internal. Yeah.
Okay. Is this better?
Yeah, that's better. Thank you very much.
Okay, no. Sorry for this. So we consider these numbers a sub I, which count the number of code words with weight I. Okay. And put together all these numbers in what is called the spectrum, or the weight distribution of the code. These are the frequencies, okay? We're counting how many times a weight appears as in the code. Okay, and we can define, the weight enumerator, which is a polynomial having these numbers as coefficients. Well, we are going to talk about cyclic code, but we need the trace representation. So we fix a generator of the field and consider the polynomial h, which is going to be the check polynomial of the code. And suppose these are the factorization into irreducibles, okay? For each j between 1 to t, define these elements, g sub j, to be roots of these irreducible polynomials, fix the order of these elements and sub j, and the minimum positive integer mj, such that q to the mj is going to 1 mod the order, okay? So this mj is the degree of the polynomials, and if we fix this number n, where delta is the GCD of these numbers, this number here. So using the Del Sartre theorem about norm and traces, about the duals and the traces, we have the query code C defined in this way. The code words are given by the traces. These traces, these are the trace function from this field to the base field, okay? And this is an NK cyclic code with check polynomial H, okay? And the dimension K is the sum of is M1 plus M2 plus MT, okay? Well, what is known about the spectra of cyclic code? There is a nice survey of Ding Li and Yue from 2015, which shows the progress in this problem in the last years, okay? And using different techniques, for example, exponential sums, such as Gauss, Klosterman, etc., special nonlinear functions, bend function, perfect nonlinear function, almost perfect nonlinear functions, quadratic forms, Hermitian form graph, Cayley graph, etc. In two works, Feng and Luo computed the weight distribution of some cyclic code of length n associated with zeros, with this set of zeros, and with this set of zeros. In the first work, they consider, M is the degree of the extension, they consider this number to be odd, and they use perfect nonlinear functions, okay? In the other work, they use quadratic forms to compute the weight distribution of cyclic code with these zeros, different, okay? In this case, for P odd, ML coprime. Okay, this method were used by other authors to compute the spectra of many other cyclic codes. Okay, we're going to do a kind of mixture. We're going to compute the weight distribution of some general families, in particular spectra of cyclic code with these zeros. These are different codes. A code with this zero, a code with these zeros, another code with these zeros, another code with these zeros. Okay, in all characteristics, and in the case with this number is even, recall here, this number is odd. And we're going to use quadratic forms. So we're mixing the problems and the techniques, okay? Well, so I recall a quadratic form on a finite field is an homogeneous polynomial of degree 2, okay? But we want to consider more general functions. So suppose any function q to the bigger field to the base field can be identified with a polynomial via an FQ vector space isomorphism. Okay, we will say that such q, such function q, is a quadratic form in n variables if the corresponding polynomial, this one that we can obtain here, is homogeneous of degree 2. Okay, so for example, I give an example. Consider this q, the trace from q to p of this x squared fixed base, an fp base of q. So every element x can be written in this way, and so we're performing x squared written in this way. We have that qx is this plus this. Okay, and now using the properties of the trace, I can write this in this form. Okay, the aj's, I can put the a's outside the trace. And so if I define this number to be c sub I and c sub ij, the polynomial represented the function qx is the following homogeneous polynomial in n variables, okay? Because if I evaluate this polynomial in A1 AM, okay, I get the Q in the sum, QX. So this polynomial representing the function is quadratic, you see, it's quadratic, homogeneous, and hence this is a quadratic form. This is the generalization. Okay, we can associate the rank and type to every quadratic form. The rank is the minimum number of variables needed to represent Q as a polynomial. These quadratic forms are classified over finite fields. They come in 3 different equivalent classes, and the classification depends on the parity. In both characteristics, even or odd, there are 2 classes with even rank and only 1 with odd rank. So for even rank, we put we consider this sign, this number, epsilon Q is 1 or -1, depending on the type. If the type of Q is 1 or 3. And this is the type, and the rank and the type are invariants of the quadratic form. Okay. So we can consider these numbers given the quadratic form now, an element beta and c. We consider this number counting how many elements in the field takes how many element x in the field are solution of this equation. Okay. In particular, if beta is 0, we are counting how many elements represent the element c by the quadratic form. And this number does not depend on the characteristic, and it is computed. One can find this in the little neither-writer book. Okay, it's this number here, nu, depends whether the element is 0 or not, but we can compute it. In the case beta is not 0, it is given by Clapper. Okay, this number is take these values, and this is the distribution. Actually, this value is taken for this amount of elements, and the second case holds for this amount of elements. Consider this exponential sum now. Okay, this is the quantity, the function that we are interested in, and we consider this exponential sum. So we now compute the distribution of these sums. Okay. Look at the possible values for B0 and not 0 are the same, but they differ in the distribution, how many times they are attained. Okay. Well, it is easy to compute this. The first sum, the second is the same. Just put the contribution of a equal to 0 here, you see, and hence by the orthogonality of the characters, when this is 0, I just counting this at 1, so I get this number, and in the other cases the sums are 0. Okay, and the result follow because I know the distribution of the number nq beta, okay, by Clapper's net. Well, this considering this is the kind of quadratic forms we are interested in. Take R, a linearized polynomial, a Q linearized polynomial, and consider the trace of x Rx. This is a quadratic form. There was some talks, previous talk, where where these were considered. And we are interested in the simplest case, I mean, when the polynomial is a monomial, okay? So this is the quadratic form. For this quadratic form, we can say more things. Considering these notations, ML, this, and epsilon sub L, this, and consider the powers, the Q to the L plus 1 powers, we have Clapper results. What is important here is that this quadratic form is always of even rank, okay? And here, depending the cases, we have the type and the rank, the type and the rank. This is what we need. And in the case Q odd, we need more notation. I don't want to get into the details, but the same for Q and odd power. In all different cases, we know which is the type and which is the rank, okay? The type and the rank, sorry. The type and the rank, the type and the rank. So let us consider the cyclic code. First of all, fix a subspace of Q linearized polynomials, okay? L is generated by all these monomials. And with this family of Q linearized polynomials, define the following code. Move for every linearized polynomial, take this quadratic form and move, evaluate on the X, on every X on the field. And this related code this is the original one, and then you add this B element here, this beta, and this beta X plus B. So we have the obvious contentions. CL is contained in all of these, and CL2 contains all the others. Well, these codes are in fact cyclics, cyclic code. For instance, if we fix alpha a primitive element of the field, then the code word CR, which is given by this, can be written in this way, using every X is a power of alpha. Now, the cyclic shift of this code word is just move. Okay, here the index moves from 0, runs from 0 to Q to the m minus 2, and here from 1 to Q to the m minus 1. So this is a code word CS. If we take S to be this polynomial, it's just multiply by this element and move a little the polynomial. Okay. But anyway, this is the shift is another word in the code. So these codes are all cyclics. Okay, we will say that the family of quadratic form, a family of Q linearized polynomial is an even rank family if every quadratic form of this type, moving the polynomial, all are of even rank. Okay. In this case, we know that by Clapper result that the type of the quadratic form is either 1 or minus 1. Okay. So we can define these numbers given a positive R. We can define the sets. Okay, the set of 4 polynomial of rank R, and we distinguish between the quadratic form having rank R but of type 1 or of type 3. Okay, we denote by M the cardinalities, And finally, consider the set of all the possible ranks in the family. Okay, all possible rank of the quadratic forms Q to the R attached to every cube linearized polynomial R in L. Well, so we can give now the first theorem. Consider, well, this is for these two codes, CL and CL0. I recall the definition. CL is this code, and CL0 is adding this B. Okay, so consider, as we said, a family of Q-linearized polynomials. If this L is of even rank, okay, every quadratic form associated to the polynomials is of even rank, then these codes, we know they are cyclic, but have dimensions m to the m times s and m times s plus 1, and the spectra is given by the following tables. Okay, the weights depends on the rank R, and okay, I have two types. Okay, I102 takes into account the different types. Given a rank, I have two types, 1 and -1. And this is the frequency. Here, this is the frequency, but I do not know in general how many ranks, which is this number. It's difficult in general to give this number explicit. For the second code, CL0, we have this distribution of weights, okay? The weight and the frequency. Okay, a sketch of proof. Well, the weight is the number of elements such that CR is not 0. So if you recall the definition of the word, which is given in terms of traces, now this is this quadratic form. This is trace of X Rx. So we are counting how we subtract the number of elements such that this quadratic form is 0. So we have this expression. Analogously for the other, for this more general weight for the other code. So we have, we know this distribution, we know these cardinals, and we get this in both cases. Now, if QR has even rank R and type ER, then we have, because we know the distribution of these numbers, okay? We have these and these using previous results. In these cases, this is the first one is for the first code, CL, and the second one, when B is different from 0, is for the code CL0, okay? And okay, from these facts, using the numbers M sub R, M sub Ry, and the set R sub L, we obtain the weights and frequency given in the table, okay? Because this number count how many, this is the set of possible ranks R here, and this number count how many of these are of type 1 or 2. So we get the tables, this table and this table. Well, we now do the same for the other two codes. So suppose we have a Q prime number, M a non-negative integer, and consider this again the family of Q linearized polynomials in FQ to the n. Well, this is a technical condition. If L is an even rank, again, an even rank family, all the quadratic forms have even rank, then these cyclic codes have these dimensions, and the spectra is given by these tables. Okay, now we have more possible weights. Here, for every rank, we have this expression here. Here is the rank R, and the type, depending, here this is a plus or minus 1, here is a plus or minus or plus 1, and this is the possible, the distribution, the frequencies. This is for the first code, and for the second code, we have even more possible weights. And well, depending on the family L, which is, it's very general. If you fix an L, perhaps you can compute explicitly this expression here. Okay, this is explicit, but more or less because you don't know which are the possible R's. Okay, so we have a general expression, but this is not explicit. Well, the proof is the same as before. You consider the weight of the words. Now we have this extra, because this is the definition of the code CL1. So the weight of the code word is the number of words, of non-zero words, minus how many X. These are the zero coordinates. Okay, I'm counting the zero coordinates here. Again, using the exponential sums, I can count this in this way, because when this is 0, I count in something, and with this is different from 0, with this expression is different from 0, the whole sum vanishes. Okay, so rearranging a little this sum, this summation, considering here if X is 0 or not, and taking into account these details, this sum here is what we call SQR, is the exponential sum SQR. And we know the values of these sums, and well, putting these values here, we get the weights, okay? And also we have the distribution. If you let me go back for a while, sorry. You have here the distribution of these exponential sums, the values and the distribution. So we get the tables with a little more work. I'm summarizing the results. Okay, and we can compute also the complete weight enumerators, but I think I'm not going to get into the details of this, but we can compute also the complete weight enumerators with similar formulas. In this case, for CL. Okay, so up to now, we consider general codes associated to general families of linearized polynomials, but although we get the expression for the weight distribution, these expressions are not explicit, okay? Now we try to explicitly compute something, so we fix the simplest family, which is the family generated by this monomial, okay? So the quadratic form are all multiples of this one. In this way, we have this irreducible cyclic code now associated to this particular L. Okay? this code, in this particular case, give rise to this code. Okay. We'll compute the spec of these codes using previous theorems and tables, but explicitly computing the rank distribution of L. Okay, which are the possible ranks and the types, and how many, which is these numbers, which are these numbers. Okay, so consider the reducible cycle code, CL and CL0, having check polynomials, the minimal polynomial H sub L, the minimal polynomial of this element, and CL0 has this check polynomial. Okay. So again, by Del Sarte's theorem, this code can be described as trace code in this way. Okay. We just add B here to the words of CL. And so in this case, we can give explicit the parameters more explicitly. Let Q be a prime power such that and ML two positive integers such that L is less than M over 2, and suppose this number is even. Okay, so the code CL is an NMV code where N is this quantity here, V is this number, and small d is this thing here. The distance is difficult to write. The distance d is given by this expression where d prime has different expression depending whether this number is even or odd. Okay. On the other hand, the other code have similar parameters. The dimension is one more, and the distance now is given, the minimum distance is given in this way, where d bar is again has two expressions depending whether this number is even or odd. Okay. The weight distribution can be explicitly computed now because by Clapper's results, now we know which are the possible ranks. Okay, so now we have these weights, this weight. Here we have this weight and this other weight, and with these frequencies. For the weight distribution of CL0, we have more possible weights. Okay. This is a two-weight code. It has only two weights. This is 1 or minus 1, depending the parity of M sub L, but this is fixed. The same here, we have 5 possible weights because these quantities are non-zero. Okay. Again, the sketch of proof is the following. We have this family. So the possible polynomial are just these things. So they are all multiples, and the associated quadratic form is this one. Okay. One observation is that these codes are obtained as certain copies, concatenated copies of this one that we studied before, of this one that we are considering now. In terms of weights, this means that the weight that we want are, we have this relation between the weights of one code and the other. So by Clapper theorem, recall that all these quadratic forms has even rank, and furthermore, these are all the possible ranks: 0, m, and m minus 2, the grid common divisor of ml. So we separate in two cases. For Q even, we have, well, we compute these things. In both cases, and for Q odd, we have something similar. And from this, we can obtain all the weights and frequencies. Also, from the tables, we can compute the minimal distances. Okay, if you look here, you have just to look which is the minimum weight here, and this depends on the parity of this number and sub L over 2. That's why we have this difference here, these two cases. Okay. Well, here I have an example. Take Q2, M8, and L1. So N is 85. So for instance, this cyclic code have these parameters. Okay, they have very big minimum distance, but the dimension is small. The weight enumerators, the complete weight enumerators, okay, doesn't matter. And we can do the same for the other codes. I will skip this because of time. I have 50 minutes.
So, well, you have around 9 minutes.
Okay, I will skip this.
Well, 10 minutes, say 10
minutes. Okay. We can do the same with the other code. I will skip this. Okay, we can compute again the parameters and the weight distributions. So I wanted to talk about just a little of some curves associated to this code, really to the linearized polynomial. Okay, so consider the arbitrary curves of this form: yp minus y equal xrx plus beta x, where Rx is any p-linearized polynomial over Fq. Now we are working in the extension Fq over Fp. So given a family of p-linearized polynomial, we define the family, we consider the family of all these curves. Okay, we move all the possible polynomials and all the possible betas here. All the possible polynomials and all the possible. So we want, in this family, we look for optimal curves. That is, curves attaining equality here or here in the Hasselbalch bound. Okay, minimal curves and maximal curves. And we have a general condition. If L is an even rank family, fix an R and fix a rank, the rank R of the quadratic form of this quadratic form, and suppose B is the periodic value of the. Recall this is a p-linearized polynomial, so the degree is p to some number, p sub b, p to the b. So this family contains optimal curves, both maximal and minimal, if and only if there is some polynomial having this of degree p to the b with this b, m minus r over 2. R is the rank of the quadratic form, and m is the degree of the extension. Okay. Moreover, in this case, for p odd or p equal to 2, the curve is maximal or minimal if and only if this curve has this explicit weight. This is the weight from the tables before. This code or in this code has this precisely this weight, or this other for the minimal. And for p equal to is similar. This curve is maximal or minimal if and only if the weight is, for example, for maximal, this one or this one. Okay, so this is a general condition we have, and now we can, well, the proof is just considered by we have this very known relation from Hilbert theorem. The number of points of this curve is related to the kernel of this trace. So the number of rational points is given by basically by this expression, which we know this expression here is related with the weight of the code. Okay, but we know these weights from the tables. So we want equality in the Hasselbalch bounds, and we need to compute the genus. But the genus of this curve is known because well, we have the Riemann-Kubit formula. Here is the degree of the polynomial f of the Artin-Schreier curve, which is this one. So is degree r plus 1 minus 1. Okay, and this formula holds if this degree with p is coprime, and this holds. So we have this genus and put in the expression of the genus and the okay. The only possibility here is that we arrive to have equality here. We arrive at these expressions, and this can only happen if the V is of the form of this form. Okay. Then we can compute the number of rational points, actually the distribution. We have all the cases, odd p and this number even, odd p and this number odd, p equal to 2, and we have the number of rational points are given are this, or this for some number of element betas. I know this explicitly, but it's too long to write here. For instance, for p equal 2, we have this expression. Okay, so it's the distribution. We don't know for an explicit beta which values of this, but the whole distribution of rational points of all these curves is given in this way. Okay, it can only have this value, or this value for this number of element betas, this number of element beta. Okay. In the talk of Daniela Oliveira, they consider something similar, and they can compute the distribution, but they are similar but different curves. Okay. So if we now want optimal curves in this family, for instance, Van der Geer, Van der Vloot found optimal curves for this family, but in this particular case. Okay. We have this general result for p odd and for p equal to 2. The curve C gamma beta is minimal if something happens, it's maximal if something happens, and the same. So and we know for how many elements this happens. Okay. And well, we have now an explicit example. I think I don't have so many time. Suppose we take this curve, which in particular is an elliptic curve. We are taking p equal to 2, so we are in this case. Okay, if you do some change of variables, you get this other curve. And for this one, we can compute this curve is minimal with only 9 rational points, and maximal with 25 rational points in these cases, for lambda 0 and for lambda 1 alpha to the 5th and alpha to the 10th. Okay, that is to say that this curve is minimal and these curves are maximal in over f 16. Well, these are all I have to say. These are the references. The work. This is the work you can find in. It is published this year. Okay, that's all. Muito obrigado. Here, this picture is taken in 2008. We invited Fernando to give a course on curves, maximal curves, AG code in Córdoba, and then I was in Juanito thesis in Campinas. It was a very nice week in which we share dinners and lunch and talks, mathematical talk with Fernando and Juanito. I remember Fernando was a big fan of the rock band, The Police, La Policía. And this picture is in Tarragona. Here you can see, well, Edgar, Carlos Monuera, I think this is Ferran. And this shadow is me. And in Novatuba, I saw Fernando for the very last time. Okay. That's all. Okay. I have a final announce to do.
Okay.
Sorry, just to recall that at the end of November, we are going to have the virtual Tercer Encuentro Argentino de Cuerpos Finitos. So you are all invited to participate. You will receive some information in breve, in short time. Okay.